This video is about gauge accuracy, precision, and R&R. R&R stands for repeatability and reproducibility. I think it's important to understand accuracy, precision, R&R. It helps you make decisions about what gauges you're going to use, and it helps you understand whether or not your gauges are in good calibration or not, in good condition or not. And it can help you decide what gauges you're going to use and which gauges you can't use. And I think that's all important for an inspector or a machinist to know, or anybody, process engineer. When you're deciding how you do things, you need to have a reason why. So this is what I'm going to talk about. We're going to do some key terms. Uncertainty is going to be one we're going to focus on. We'll also talk about the gauge R&R and all the terms related to that, as well as the reproducibility and repeatability definitions. So we'll go through a few examples and then we'll focus on the actual definitions of what these mean, so that when we're having discussions, when we say accuracy, we mean accuracy. When we say precision, we mean precision. So when you think about accuracy, precision, error, repeatability, reproducibility, these all apply to different situations, and sometimes people in a conversation will say one thing and mean another, and when people don't understand, it can cause a little issues. So I just like everybody to be on the same page, which is why I recommend you understand these terms. Watch this video. If you need to look up some more references, go ahead. There's plenty out there, but I'll do my best to give you the classic examples, so that when we're discussing things and I talk about accuracy or precision, you know exactly what I'm talking about. Some of these terms have multiple applications in metrology. On the one side, there's the inspection metrology side, and another one is going to be the calibrating and traceability side. So some of these have overlap. Some of these have slightly different definitions, but for the most part, the concepts are the same, but the precise definitions can be a little bit different. So for example, calibration, measurement systems, analysis, gauge selection, gauge R&R, ANOVA, variance method, statistics, they're all going to use these terminologies, these terms that I'm going to be going over. But we're gonna make sure you understand each one. So to do that, we're going to use the classic example when we're talking about these terms as a target. So imagine it's either a shooting target or a dartboard like I had on the first slide, and you're trying to hit the center. The center might represent your tolerance and how close you are to center. It might represent the condition of your gauge. It might represent how accurate, but let's start with an example. We're going to walk through this goal, hit the target in the center 10 consecutive times, right? So bullseye 10 times in a row. We want that in inspection. It might be difficult in real life to throw it at a dartboard, but in inspection, we want to hit that bullseye every single time so that we're making sure we get good parts. So let's talk about the first one. The first term I'm going to talk about is precision. What does that look like in our bullseye example? The first image on the left, you see the shots are all spread out. There's no real pattern. There's no real grouping. They're all just kind of all over the place. So I would say that grouping has no precision and no accuracy. It's not accurate because it's not really anywhere near the center. One of them got near the center. And there's no precision because they're not grouped together. Precision is going to be, well, how well do the values repeat in successive measurements with the same conditions? So this isn't repeating. If I'm applying the same conditions, like if I built a robot to throw the dart at the same time or shoot the target at the same time, it's all over the place. It's not repeating. The middle has the better precision and no accuracy. So the grouping got smaller, but it's not any more accurate than before. It's still off center. You can see that it's kind of closing in on a center point by getting a smaller grouping, and that center point isn't near the the bullseye. One or two shots actually did get in the bullseye in the process, and that's kind of incidental. The last image on the right side, I would say good precision and a little bit better accuracy. That's kind of a judgment call whether the accuracy improved or not. But I would say compared to the big giant blob and where it is now, it's at least consistent precision. The grouping is tight, it's repeating. Now you've got to work on your aim. You've at least solved the repeatability problem, but now you've got to work on your aim and try to get that, hit that target in the bullseye. So I like to start with precision so that we can do an accuracy example. Following with the same concept, the one on the left, good precision, right? We've got a nice tight grouping of targets, but there's no accuracy. It's way off on the outside and the bottom, nowhere near the bullseye. The second, the picture in the middle, your precision has already been good, but your accuracy is getting better. You're improving your aim, you're getting closer to the bullseye. And the third target, showing good precision and good accuracy. Every single target is in the bullseye, exactly what we wanted in this example. So in metrology, accuracy asks the question, how close the measured value is to the true value, the known true value. So if I took an example, I'm going to use a gauge block. I know this is 1 inch, right? It's calibrated. It's been verified by an outside company. This is dead on balls, 1 inch. So when you want to compare a micrometer, we'll do the 1 to 2 micrometer. When you want to compare a micrometer to it, you're gonna ask yourself, well, how close to center am I on that target? And when we look at our micrometer, I'm pretty much dead on center. Right there. So I'm reading 1 inch pretty much exactly, which means it's in good calibration for this point. I'll talk about calibration in more detail later in another subject, but if I did have a bad condition, I'll give you a fake kind of condition. If it stopped above 1 inch, and then the next time I checked it, it was below 1 inch, and then it got all over the place. Every time I check it, it's just not repeating. It's not accuracy. Those are accuracy and precision problems. But how close it is to 1 inch is the accuracy part of it. And that can apply to a calibration, or that can just apply to a measurement. How close are you to the true value? Now, we don't always know the true value, right? In an inspection, you're trying to determine it. So we use a calibration check to verify our tool is good, and then we assume when we use that tool, we get the known value of the part, whatever part we use that tool to measure. Okay, so next concept, probably a concept you may not have heard of. You know, everybody, I think, familiar with accuracy and precision, at least in real life, but uncertainty, that's a new one. The analogy that I apply to the target example is how clearly can you see where the targets hit? Okay, so this doesn't have 10 points, it only has 1 point so that we can illustrate uncertainty. But on the left, you have just a very blurry target and a big, large, blurry purple zone where the target hit. And that's a big area. It could have hit anywhere in there. You kind of get like a heat map sort of, you can kind of infer where it is, but in terms of uncertainty, it could have hit anywhere where that purple shadow is. So it has very high uncertainty. And that might correlate to a caliper's accuracy, because we know, if you watch the other videos, the caliper is one of the more, how do I say this? One of the least accurate precision gauges that we have. So compared to everything else, this is going to have a bigger uncertainty. The picture in the middle, the uncertainty is getting a little better. You can see the size of the unknown area has gotten smaller. The target's a little clearer. In reality, you know, the blurry target is not exactly accurate. It's more of just the blurry purple region. The target, now that I think about it, really should be clear at all times, because targets, you know, your requirements are clear. But I would say, you know, just for this example, you just focus on the size of the purple target, or the purple mark. And so in the middle, it's getting clearer. You can start to see it's not that big, huge blob anymore. It's a more tightly defined one. And then on the right, you finally get to a low uncertainty where you can really kind of see the target, or see the point. It's still a little bit blurry though, right? It's not entirely clear. And I left it that way to illustrate the point that we're never going to be 100%. We're never going to know with absolute certainty. There's always some possibility for error, for the fact that we can't know exactly the true, yes, I verified it, but I don't have anything. I'm not omnipotent. I don't know everything. I don't know if I measured this correctly. I don't know if there's not some micro errors that I'm not picking up with something. So what I want you guys to remember is, nothing's perfect. Nothing you do. There's always a little bit of uncertainty. No matter it's $1 million CMM in a very controlled environment, you'll still see it'll have an uncertainty error that the manufacturer has to state and measure and use as a marketing tool, really, to compete. The less uncertainty you have, the better gauge you have, but it's always going to be there. So in metrology, what I like to say, after a measurement, how certain are you that the value, after a measurement, how certain are you in that value? What is your plus or minus spread? That is kind of what is your blurriness factor. So my analogy is going from a steel rule to a caliper to a mic, right? Each time you get more certain about your measurement because you get more accuracy, more precision. They work hand in hand with uncertainty. But we really focus, and a lot of gauges will focus on uncertainty. So this is what we're talking about. So when we try to map all these terms together, I came up with this graphic to sort of explain what's going on. So what I want to do, I want to use an example. If you've got the PM02 print downloaded from the Pragmatic Metrology website, you don't need it, but I'll say I'm going to measure the 3.210 distance with a caliper. And if I do it 6 times and we take a look at what we get, we might get something that looks like this, where we have 6 dots. And so we have on the graphic there, the range from red to red represents your tolerance, right? Where that's your tolerance zone. Your dots need to land somewhere in that tolerance zone in order to be okay. But how does, just being in tolerance, that's great. That's what you want. But if we zoom in on what's actually happening, where is the precision, where is the accuracy, and where is the uncertainty? So let's start off with the precision, the way we started. So the grouping of my 6 points, yeah, there's some variation there, right? I don't know how to quantify that, but if you needed a number, let's say it's 3 thousandths. You've got a few points that were the same, and you had one lower and one higher that really spread out the precision of that grouping. And then when we talk about accuracy, well, the center line of that accuracy will be the red dotted line there. And how close is that center line to the true value? The one that we kind of know, is true. Sometimes we know and sometimes we don't, but for the example, we're saying it's the true value. That's how accurate it was, and maybe that's if my precision was 3 thousandths, and if that is drawn to scale, heck, that could be 5 thousandths of accuracy error. It could also be that this is so zoomed in, it's only 1/10,000th accuracy error, and it's only maybe 2 10,000ths of precision spread. It depends on how far you're zoomed in, and which factors into which gauge you're using. And then the uncertainty ratio I have there in purple. And what that means is, the manufacturer, kind of independent of precision and accuracy, just looking at kind of the center line, the red center line of where the grouping was, the manufacturer is going to state an uncertainty. And they're going to say, well, not necessarily the manufacturer, I would say. Not the manufacturer, but, it's going to be like, yeah, whenever you measure something, if it tells you it's at one location, well, you've got a spread, right? It goes back into that blurriness factor. And how blurry that is depends on how good the gauge is. And it really is independent of precision and accuracy. The uncertainty is just based on, with a caliper, you're going to get a bigger uncertainty, and with a micrometer, you'll get a smaller uncertainty. In a few minutes, I'll talk about how that's determined. But it's just one of those, when you start to use gauges a long time, you're using it over and over again, occasionally you're going to be like, wow, that was really weird. Like, instead of it's going to be way off, and you're just not going to know why. And it's because it's one of those situations where the uncertainty just played a bigger role than it has before. So uncertainty is a combination of the instrument and the fixture and the environment and the calibration and the sampling and the analysis. The more you can control that, the better resolution, for lack of a better term, that image resolution you get. And when you're talking about, what can you control and what can't you control, accuracy, you can, through calibration and repair, put that distance to 0 or make it smaller. And same thing, precision is sometimes an inherent part of the gauge, but sometimes precision is due to a gauge in poor condition, which you can repair back to a level that meets the original specification. But it's hard to actually improve precision. It's kind of an inherent property of the gauge, just like uncertainty. But accuracy, you can do a little bit through calibration. So yeah, in this example, what's going on? Something's wrong. The uncertainty zone should contain both the measured average and the true value. And so that means your measured average, what I measured as an average, is not within the range of the true value relative to the uncertainty zone. So we need to fix this. And I think calibration would fix this error to where that blue accuracy dotted line and the red average dotted line would end up on top of each other or pretty darn close. And then the uncertainty zone would move with it. The dots would move with it. And then, probably the gauge is out of spec for its calibration tolerance. Every gauge has a tolerance for how well it measures something. It's never going to be dead on perfect, right? It's going to say, well, if you're within 50 millionths, we're going to say it's calibrated. Or if it's repeating within 10 millionths, we're going to say it's repeating well enough to be calibrated. Those numbers, that I just made up some numbers, but there are standards out there. So in this case, repair might be necessary, but repair is not going to shrink that uncertainty zone. It's just an inherent nature of the gauge. So next up, we're going to jump into the R&R part of the lecture here. So Gage R&R, if you haven't heard about it, you have repeatability and reproducibility. So repeatability is the same as precision. It says how closely can you repeat a measurement with the same gauge under the same conditions. So first of all, what's same gauge and same conditions? Well, same gauge means physically the serialized same gauge. Same conditions means same temperature, same technique, same person, same inspector, same operator. So everything's the same. If I measured this half-inch, looking for a half-inch, this half-inch gauge block with the same technique 5 times, what do I get 5 times? What is the spread? What is the average? Reproducibility becomes, can you reproduce a measurement using the same gauge with different people and technique over a period of time and possibly environmental changes? So this is kind of like, how bulletproof is your system? Does it only work with when I do it, but not when another inspector does it because we have different techniques? Does it only work at one temperature, but not another? Most of the time when we're talking about inspections, we want consistent temperature over long periods of time. So if it's not reproducible at different temperatures, that's normal. Most inspections are not reproducible at different temperatures, but so typically we'll kind of control for that. But you're talking about, changing up some of the factors and how reproducible do you get. So for example, have 3 different people measure this block with the same micrometer. What do they get? What are those? A lot of times I've been in shops where it's like one guy measures it, it's imprint. He's like, I'll get my buddy to verify me. He checks it, it's not imprint. He asks the inspector. It's different from the other ones, but it's imprint. And so it happens, sometimes in these really tricky situations, you kind of want to rely on multiple people to help verify something. Sometimes it's the gauge, sometimes it's the technique or the person. So you're trying to narrow that down. But that last bullet point in bold, gauge R&R is critical. If you're not reproducing, you can't really trust the method. If you're not repeating, you can't really trust the method. Something probably needs to be fixed and calibrated. Because when you have gauges in good calibrated condition, they will repeat and reproduce. So here's some other terms related to gauge R&R. You have bias, and bias is sometimes described as accuracy is sometimes described as the lack of bias. So if you're at that target and you're always shooting up, you could say you're biased up. And when you're hitting a bullseye, you would say, yeah, there's a lack of bias there. I'm always hitting the bullseye. And that's kind of, bias is like a systematic, repeatable issue. For example, when your micrometers don't close on 0, which is fairly common. I've done these videos. I've used the micrometer in multiple videos, and I've had to calibrate it because it wasn't closing on 0. But if it's not closing on 0, that means there's a bias, right? If you're not starting at 0, it's very likely all the other measurements you take will be biased the same amount. Right now it's actually reading pretty good. I must have had a tiny scrap of something on the end. So when you're talking about a biased micrometer, calibrate it, check it at 0, check it a couple other places in the stroke, and you should be good. The next one, stability. Well, that becomes, is the gauge affected by temperature or humidity? Do bias only show up in certain environmental conditions? Could even be like gravity-fed orientations. I've had a gauge that was loose and I didn't realize it, and when I was holding it horizontal, it was fine. But when I started to go vertical with it, I was getting some bad. It was just a gauge in bad condition. So can you only use that gauge at all times under certain conditions? Sometimes You know, if you're measuring the same part over and over and over again, that part where you rotate the nut on the ball screw in here, that'll wear, and the rest of it'll be fine. The rest of it'll be real tight and smooth. But when you end up going back to that part that you check maybe 90% of the time, it'll get looser and looser and looser just in that spot. So that can be a form of stability if you wear a spot in one of your gauges. Next one, linearity. So a lot of people, when they're using a gauge, they assume that whatever error exists, it's constant throughout. So in this example, I have a graph, and if you look at maybe the horizontal dotted line, that would represent a constant error, no matter where this gauge is in its stroke, whether it's close to zero, a quarter of the way, halfway, 3/4, or all the way open. You're assuming that the gauge error is constant, that whatever positive, there will always be some error, as I've shown on the graph, but whatever it is, it's constant. And that's not always the case. So sometimes, like I mentioned, if it's worn in one area, you'll get more error. Calipers can be really susceptible to that. Same with micrometers. Height gauges get used a lot, and the part that gets the most error because there's more gravity, heavier parts wearing, pulling down, they'll wear more in certain spots in the stroke. And the danger is a lot of people will not check, right? They'll check it at 0. And in this example, okay, there's an acceptable amount of error. It's less than 1,000th. Sorry, it's less than a 10,000th. And I'm not going to do much better with my hand calibrating. So I'm going to go forward. Well, if I didn't check halfway through, I'm getting 2 10,000ths of error. 3/4 of the way through, I'm getting over 3. And so it must be that there's some error. There's a lot of, I've probably been opening and closing this around a certain spot a lot and wearing it. And the danger is I only checked it at the beginning. So if I had a tight tolerance part, maybe I only have 2 or 3 10,000ths of error, and I start using it mid-stroke, I get more error here. So the way to remedy that, grab a gauge block that's partway through and check multiple places. This is a 3/4 gauge block. And so I told you it was, let's just go through it. I'll grab all the blocks. Let's see. Let's check the condition of this micrometer. So I will start at 0. And I will allow the camera to focus a little better by moving away some things. Okay. I think it focuses a little better when it's less on there. All right. Reading a 0 there. I'm telling you, it's perfect. I can barely see it's a little bit above. Okay, it's not quite perfect. Now let's check at a 1/4 inch. Ooh, look at that. Look at that. It's no longer perfectly 0. I'm using my touch. I feel pretty good about my touch. I'm going to wipe off the block and wipe off the handles again. Let's check 0. Actually, it's changed. So as I've mentioned in the micrometer video, a great way to clean off micrometers, grab a piece of paper and drag it along. And that will wipe off anything. So where are we at? We're back to 0. Okay, back to 0. Let me clean off these other ones with my finger. There may be a little oil, maybe a little dust, chips. Let's see what this looks like. So this is a 1/4 inch by touch. And I'd say it is even still just a hair above, probably very close to where it was before. Sorry about that. So just a hair high. Let's do the half. Let's see if this linearity maintains. So I'm going by feel. How does that look? That looks pretty much the same. It's holding just a little bit above. Might have grown a little bit, but I'm not too concerned. It's still very small error. It's not like the example I had in the PowerPoint slide. Okay, I'm going by feel. Again, that looks pretty good to me. If you want to check the secondary camera feed right here, you can see it much clearer. It doesn't show up very well on the big monitor. And I'm going to do the 1 inch. So this is what I recommend you do every time you do an official calibration, as well as when you have a really tight tolerance diameter that you might be measuring or distance. Verify as close as you can. If I'm measuring an 875, set up an 875. If you're measuring a 442, set that up. You can use the Joe blocks to build up that stack. So I'd say this one's in pretty good condition, considering all the use it's gotten. So if I saw a difference, I would have seen some difference in 0 as I checked it along the stroke. So in this case, I would say it matches that dotted line. It was fairly consistent. It might be sloping upward a little bit, but otherwise it was pretty good. Then we're gonna close off with a couple. Sensitivity. So sensitivity is one that, I think about calipers when I think about sensitivity. So I say, or anything digital, what is the smallest increment of change the gauge can sense? So for example, how far does the gauge move before the display changes the last digit? Did you know that a lot of these calipers can sense movement? Calipers, height gauges, CMMs, they will sense a movement, but they won't display a change because they're not accurate enough to display a change. So they'll know it's moving, but these have scales in them that when it's in between, for lack of a better term, the hash marks on the scales, when it's in between, it just won't display anything until it reaches the next mark that it can accurately display. So a lot of digital gauges work that way, whether it's optical or magnetic. It can actually sense a little bit before it displays it. So sensitivity really doesn't affect you, but it does. Sometimes you measure, I have five Joe blocks here. I have 5 Joe blocks here that are all 1/10 of an inch different, right? These are the 10th different ones. So I'm gonna measure each one from 0.1001 to 0.1005. We'll do them in order. So here's the first one. I'll do it with my caliper. 0.1, and it's kind of showing that, yeah, it feels like it's somewhere above 0.1, but not quite to 0.101. I'll do the 1002. This is 2 10,000ths above 0.1. It shows the same thing. You can see that. Here's the 3 10,000ths. Okay. No, still showing 1.1. Here's the 4 10,000ths, still showing 0.1. Here's the 5 10,000ths, still showing 0.1. Oh, here's 0.101. So it may have it may be just a tiny bit out of calibration, or it could be that I just need to clean it off. There we go. There we go. So it's fluctuating. It's kind of in between measurements, and as I vibrate it, it's moving. But if you saw it, it was sensing some change, but it wasn't quite displaying it until it reached a point where it felt comfortable displaying it. All right. Oop. Let's jump back into our presentation, and we're going to wrap this up soon. All right. So resolution is really important. Resolution is going to help us understand uncertainty ratio. So in another video, we really go in depth on uncertainty ratio and error. And resolution is basically, well, what's the smallest increment you can see? What on the gauge itself? What's the smallest increment that the gauge is displaying? With a caliper, it's 1/1000th of an inch, 3 decimal places most of the time. And with a micrometer, it's 1/10,000th of an inch most of the time. With other styles of micrometer, it may be different. It might still be 1/10,000th, or could even be 2.5 10,000ths. I've seen some whole mics that way. But it's just, what is it displaying? And that's the difference between resolution and sensitivity. My point at the bottom there is sometimes they're not the same. Sometimes the gauge is sensing something, but it's not displaying it when it's digital. And then, the most important ones are going to be the gauge R&R, accuracy, resolution, accuracy, precision, and uncertainty. But these are a couple that are kind of related. So I want to thank you guys again for watching and watching these videos. I hope you're enjoying them. I hope you're learning something. I do want to quickly thank the Laney College in Oakland for providing parts and tools. A lot of the tools that I've been demonstrating they've let me borrow for these videos, and they have a really great program, the machine technology program at Laney. They've got classes on not only metrology and quality control and inspection, but also CNC machining and manual machining, blueprint reading, 3D CAD modeling and making blueprints, mechanical drives, many other courses. They offer certificates if you take enough courses in a certain category. They offer associate's degrees and even some apprenticeships. They're connected with businesses in the area to help people finish their apprenticeships. So please check out Laney College in Oakland if you're in the Bay Area. They offer classes, nights, weekends, days. They have something for most people's schedules. And please check out my website, pragmaticmetrology.com, for more videos, for resources and blueprints and parts. You can download the blueprints, you can download the CAD models if you want to follow along with me. So thank you, and I look forward to seeing you guys for the next video. Bye.